Hello everyone, so welcome to lecture 40. So this will be the last lecture on this current module on thermodynamics, phase transitions and statistical mechanics. The basic idea was actually to look at equilibrium properties and their origins, both from a thermodynamic framework and a statistical mechanics framework, and then later we started doing phase transitions to understand that so at the verge of phase transitions these equilibrium properties actually enhance or depress depending on which property you are trying to see. The fluctuations enhance, and properties that are related to the fluctuations of some sort of order parameters, they would enhance, right. So we stopped at that point. We were looking at we looked at Landau phenomenological theory with one particular order parameter, and that order parameter is polarization or spin. You can use it, so it works for any order parameter in that context. So you can have two order parameters. That is a more complex way of looking at Landau theory, but I just gave you basic details of Landau theory. It is a phenomenological model, and we solved this quadratic equations, and we saw so because of so we saw at the phase transition where the polarization becomes from ordered phase to a disordered phase, right. So the susceptibility enhances, right. So yeah, or so it does not need to go from ordered to disordered, it can also go from one type of order to another type of order, and you will define an order parameter, an appropriate order parameter, and there also so you will have enhancements of something like susceptibility, right. So these properties enhance. Now the question is okay, so to enhance these properties we stopped at a point where we said the phase diagram of water and the phase diagram of a ferroelectric or a ferromagnetic material so are quite analogous, right. So we said in water I have, this is the pressure axis, this is the volume axis, and this is the temperature axis, and so the phase diagram looks a bit complicated with all the different isotherms and isobars and things like that. But if we slice it into PT, right, so which is equivalent to our H versus T, or H is the same as electric field, H is the magnetic field, E is the electric field, right. M is magnetization, P is polarization, right. So we saw analogies that pressure versus temperature will be the same as H versus T, and so you have this, you have so this is like the water phase, this is like the vapor phase, and both of them go into some sort of a superfluid phase, right. So the polarization up is like the water phase, polarization down is like the vapor phase, and so they have a specific phase boundary, but this phase boundary disappears, and so it becomes a super fluid like phase, and that is equivalent to my para electric phase, right. So that is the analogy, right. Then if I look at polarization versus temperature, that is equivalent to looking at volume versus temperature also. So essentially I am just looking at for critical points, right. So I will look at water and water vapor, right. So I will not bother about the ice phase, right. So I have two phases which are water and water vapor, and the superfluid phase. So superfluid phase, this is like the ferroelectric up phase, this is like the ferroelectric down phase in terms of analogy, and this is beyond the critical point, the superfluid phase is like the paraelectric phase, right. So if we are actually going to look at that, that is also a dome like this, right. So if I am here at this temperature, so I have both water and vapor which coexist along this coexistence line, but as I keep on going towards this point, so there is no difference between water and vapor, both of them would so transform into what is called a supercritical phase, a superfluid phase, right. So that happens at the critical point, and it is very similar to what we have here, right. So if I am somewhere here, right, so I have the polarization up or polarization down, right, so in temperature, and if I do not do anything to the material, they should coexist together. But if I come and this is the coexistence line, and if I am at this temperature, so both polarization up and polarization down will fluctuate off to a very disordered phase. So this is a disordered phase, and what you have here is an order to disorder phase transition. So we are saying at this point, right, so this is or close enough to this point, that is where so the polarization goes with temperature as this, right. So it just drops down, and it is dropping down as so here so if I go by the mean field or Landau theory, it should drop down as minus t power half, and we are saying at this point the susceptibility ideally if there are no losses should go to infinity, but since there are always losses, susceptibility will go to very large values. This is without losses. With losses it goes to very high values. Okay. So, you are enhancing property, you are enhancing susceptibility at critical points or at phase transitions, right. So wherever, so we just looked at second order phase transitions. Now, I was going to show you this YouTube video, but because of copyright issues I cannot show you in this class, right. So what I would rather say is just go and look at this YouTube video. This is a YouTube video of so carbon dioxide that changes from its vapor phase or a liquid phase all the way up to a supercritical phase. So something like this at the in the carbon CO2 phase diagram, right, and then or even water also has such videos, right. So you can look at water or vapor which are at this pressure, which are being so initially I can so if I want to describe that video, initially I can see that water exists separately and vapor exists separately, right. So this is the liquid and the solid, right. So it does not matter if it is carbon dioxide or water. As I keep on going towards the critical point, which means I should increase so initially I am at let us say room temperature and so some point like this, right. So initially I am somewhere here, and from here I am trying to go towards the critical point, right. So some point on the phase diagram to critical point, that would entail increasing pressure and increasing temperature, let us put it that way. Okay. So when I am slowly increasing pressure and increasing temperature, you will see that this so this phase separation between water and vapor slowly starts disappearing, and eventually you will have a superfluid phase where this is all transparent, you cannot see anything, right. So this is all transparent. Okay. So this is superfluid phase, this is beyond critical point. Okay. But what happens while it is approaching criticality is where all the fun is. You will see that so density of water is different from density of vapor, right. So let me just write it in the notes. So I am actually describing it to you in words what you will see in the video, but the video is more illustrative. So this is water, this is vapor, and then this actually transforms into a superfluid phase where this phase boundary vanishes, right. So superfluid phase, this is beyond criticality. But what happens is so when you are approaching the critical point, you can actually see that so there are so many. So here vapor has density 1 or density 2, water has density 1, right. So your density is your order parameter, right. Now you will see that there are huge as you are approaching so there are going to be huge fluctuations in densities, right. So you can actually see that optically, because if there are you cannot really say what is water, what is vapor, the phase front starts to fluctuate a lot, right. So there are huge amount of density fluctuations which you can actually see, right, and eventually it all settles down to one phase, which is the supercritical phase or superfluid phase, right. So so it would have been nice if I can show you the video, but I would urge you to go back and see these videos and then understand for yourself what I am saying. So the way this phase transition is happening is through fluctuations. So I have to move from D1 to D2, right. So this is order parameter 1 to order parameter 2, and so my average D1 is decreasing towards D2, right. So this is D1 so this is D2, let us say, okay, as a function of temperature, as a function of so some temperature or pressure that I am changing as I go to the critical point, correct. However, what changes is right at about this point. If I look at the fluctuations in density, there are huge amount of fluctuations, which means if I take this phase front, right. So, I start creating, so this has a, this is every point here is supposed to have some density like d1, right. So, with very minimal fluctuations, but these fluctuations go to infinity. So, this is no longer d1, at one instant this can be something like d2, at one instant this can, this point can be something like so very high density, right. So, this can be icy, this can be vapory, right. So, you have all these various fluctuations that are happening. So not icy, but dense water, dense vapor, very less dense vapor. Okay. So, instead of calling it water or vapor, I am just going to say that my entire, so there is not going to be a nice phase front anymore, right. So, rather what I will find is regions which have density d1, regions which have density d2, regions which have density d3, or regions which have density d4, and so this fluctuation, the density fluctuations are infinite. Or in other words, the volume of volume fluctuations or density fluctuations, it is one and the same. So, this quantity average volume square minus of every individual unit, right. So, I can divide this into so many microscopic units, this goes to infinity, okay. And this is actually related to again a property, and that property is what is called isothermal compressibility. Again another thermodynamic property. So, that is defined as so how much volume can you change by applying pressure, right. So, if it is very compressible, this value is very large, okay. Actually it is 1 minus 1 by V of this, right. So, what is the change in volume, what is the volumetric strain generated by applying pressure? Right. And at the critical point or close enough to the critical point, my water or my H2O is beta, or which is the isothermal compressibility of H2O is huge, right. Like our former US president says it is huge, right. So, it is and at the critical point ideally beta should go to infinity, right. So, it is infinitely compressible. I do not even need to apply a small amount of pressure, will change so much in the volume, right. So, and the way this is changing from a volume 1 phase to a volume 2 phase is through fluctuations. It will create lot of fluctuations, it will create volume 2 first, right, and then slowly as you keep on increasing the temperature, the volume 2 stabilizes, and then another order parameter stabilizes, right. So, that is my supercritical phase. So, initially I have d1 to d2, and then eventually I am going to settle down at a phase which has a uniform density, right. But this transformation is happening through huge density fluctuations, right. I have d1, d2, d3, whatever densities you can think of are there in this intermediate region where the transformation is happening, okay. So, that is how the phase transition happens, that is how the second order phase transition happens. Second order phase transitions happen through fluctuations, large fluctuations of order parameters. Right. In case of polarizations, right. So, initially I have polarizations which are all pointing up, let us say, then as I increase the temperature, okay, some of the polarizations are thermally dancing a bit this way that way, right, but average polarization starts to decrease, right. But at the phase transition, right, so I will have one volume with polarization this way, this way, every possible way, right, and these are also dancing around, right. So, these polarizations are dancing around with time. With time, all these micropolarizations dance around vigorously, okay, and eventually they all sort of freeze down to a completely disordered polarization state, right. So, this is the so these are dynamic, this is very dynamic, and eventually so the dynamics reduce and this is disordered, but fluctuations are less, okay. So, the polarization goes to 0, but if I look at the susceptibility goes to almost infinity, right. So, I mean not almost infinity, there is enhanced at the phase transition. Okay. So, now we have a recipe to create materials with large susceptibilities, right. Similarly, any sort of property which is large, right. So, it can be electrical, it can be electromechanical, right. So, what is the recipe to create materials with large properties, right. So, again we will consider our favorite property, which is susceptibility. So, susceptibility as an example, okay. So, we have to be so if we are at the phase transition point, susceptibility is large, right. But if the phase transition is at 600 degrees Celsius, it is useless for me at room temperature, right. So, I would want to search for materials, and susceptibility needs to be enhanced at room temperature, that is my problem, right. Let us say this is my problem, needs to be enhanced at room temperature. So, my solution is, let me search for a material which is close to phase transition, some sort of phase transition, and by phase transition here I mean phase transition that changes from order parameter 1 to order parameter 2, right. Let me search for a material which is close enough to such a phase transition at room temperature, right. That is one strategy, right. Now, for example, I have if I go to this slide here, I have a material called this is a lead based material, lead scandium niobium oxide, right. This is what is called PSN in short form, lead scandium niobium oxide. This is a perovskite material. We looked at what perovskites are. Lead sits in the A site, scandium and niobium both of them can sit in the B site, right, but both of them are randomly aligned, or so they can be orderly placed along the B site of the perovskite, and oxygen sits in the anion site or the phase centers, right. So, this is the oxygen site, okay. So, this is my perovskite structure. So, whenever I say perovskite structure, so you can go back and look at Vesta, but by the end of this course you should exactly imagine what the perovskite structure is, okay. Then you see, so if I am looking at its epsilon or or susceptibility, right. So I am going to interchangeably use epsilon and susceptibility. You see that susceptibility actually peaks, right. So, near the phase transition. Do not worry about the blue and red, one is a cooling curve, one is a heating curve, but about room temperature I have a peak in susceptibility. Okay. Okay. So, this is if I need a material of very high susceptibility at room temperature, I can use this, right. But so why only confine yourself to room temperature, right. So, let us expand the problem. Why confine to room temperature? So, PSN is a solution. Let me write the solution in this color. So, but why confine to room temperature? Let me say I need a material, or I need to design a material with large susceptibility over a range of temperatures, right. So, for example, if I plot chi versus temperature, it should go up, but it should sort of be flat in these temperature ranges, right. So, my device operates in a different in several temperature ranges. So, I need this sort of a flat profile. Okay. So, now let us imagine how am I going to get this flat profile, right. So, let us imagine that I make a material some sort of a composite of several materials, right. So, I am plotting chi versus T, but all these materials. So, first one has a phase transition at this temperature, second one has a phase transition at this temperature, third one has a phase transition at this temperature, right. So, this is 1, 2, 3, 4, 5 and so on and so forth, right. So, I use roughly 5 my material should have 5 different phase transitions, let us say, in close vicinity, in temperatures which are close enough to each other, right. So, then I can have chi versus T, the net. So, this is for chi 1, this is chi 2, this is chi 3, this is chi 4, chi 5, right. So, I can make a hodgepodge of all these things, very simply put, right. So, this is what is my hand waving design principle, if I may ask that question, where I can probably get a susceptibility curve like this, right. So, in these broad ranges of temperatures I have a large susceptibility. Okay. So, so how can I do something like that? Let us say, so for example, look here. So, this is barium tin titanate, right. So, this is called BST. BST is a very good dielectric material. Now, BST also has some sort of a phase transition, right. So, depending on the composition X that I use, the phase transition keeps changing its position. Okay. So, this is x equal to 0.8, this is x equal to 1.105, this is x equal to 0.14, right. So, x is increasing in this direction. And with increasing in x I am changing the position of this phase transition, right. So, now the so what I am going to do is, so let us remember the x's. So, this is at 60 degrees, this is at 25 degrees, this is at 30 degrees and this is at almost 10 degrees, right. So, now I want to make a material, I want to make BST which has a large dielectric constant. Design BST with large dielectric constant in the temperature bandwidth of something like 5 degrees to something like 65 degrees Celsius. Okay. So, this is a good enough temperature bandwidth if I am using BST for some sort of energy storage applications, right. So, for energy storage I need a large dielectric constant. Okay. So, then what I am going to do is I am going to grow so let us say BST thin films, but for the first film the x equal to 0.08, and then I grow another film on the top of this with x equal to 0.1, and then another thin film on the top of which x equal to 0.14. So, I grade the composition, right. So, now BST is barium tin 1 minus x titanium XO3, right. So, again another perovskite material, but I am just grading the composition, right. So, I am grading the composition from 0.08 to 0.14. As a result, I am actually creating different materials. In some sense the interfaces also will have some role to play, let us not worry too much about it, but very naively, right. So, if I look at chi versus T of material 1, material 2, material 3, if they so I have to make it and make sure that they remain as material 1, material 2, material 3. Then so I have the first material gives me a phase transition at 60 degrees, the second material gives me a phase transition at 30 degrees, the third material gives me a phase transition at 10 degrees. So, if I combine everything so I may end up with something which looks somewhat like this, right. This will be 5 degrees, this will be 65 degrees, right. So, and I have a high susceptibility. Okay. Now, maybe I will have an issue here, right. So, because I have created a compositional gradient, right. So this is my film of barium strontium titanate which is compositionally graded, right. So, which is compositionally graded. Okay. So I do not know how to draw grading here, but let me try. Okay, so there should be some function to draw grading. Maybe let me try this. Fine, does not matter. So I am just grading it. So x is increasing, right. So from bottom to top, right. It turns out that this compositional grading, you can create it with techniques that are available now, material growth techniques such as pulsed laser deposition. With thin film growth techniques such as molecular beam epitaxy. You have other techniques such as sputtering, right. So all these are what are called physical vapor deposition techniques. I am not going to talk about them in this course, maybe there is one more course that I offer, not on NPTEL yet, in which I talk about these materials, these techniques. However, so you can use these thin film deposition techniques to actually create this graded layers. Okay. You can create them, but can you sustain them is the question, right. So I have a compositional gradient. Okay. I sort of freeze the material there, this is my substrate, this is my thin film. Then let us say I apply some sort of an electric field, right. So with a, let us say I have a gold electrode, I put a gold electrode which is gold, okay, so I can't see the yellow color, but let me try orange, oh sorry. Let me try the orange color, yes. So I put an electrode, this is an electrode, and let us say I have another electrode somewhere here just underneath the film, right. So this is top electrode, this is bottom electrode, right, and then I apply a bias between these two electrodes, because to measure capacitance I have to apply bias, right. So remember that this is a graded layer. So typically what turns out is the problem is, okay, so I have so many different interfaces here, right, but the grading of composition means, so when I apply a bias, right, so when I give some energy, right, so I am giving the thin film heterostructure, this is called a heterostructure, right, the graded thin film some energy, right. So then if I have compositional gradient, the compositional, so the gradient in composition or delta x, right, this is, or delta c, c for composition, right, the gradient in composition tries to go to 0, right, or so in other words material will diffuse from higher, or it is going to what is called migrate here, because it is under the influence of electric field and not temperature, from higher concentration to lower concentration, or material or atoms. Okay. And so so although you thought you made a material which has a susceptibility like this, so this is the desired material, right. If you start testing it, if you start working with this material by applying electric field, by thermally cycling it, right. So if you apply temperature also, all these layers, right. So even with temperature, okay, there will be diffusion and the layers will try to homogenize. And come to some sort of a chemical equilibrium, right. So although you started with this, you may end up deteriorating your susceptibility quality and you may end up something like this, right. So I mean, so maybe I do not know, so you will degrade the material with cycling. Okay. So so then what is the solution, right. So I said I have a thin film which is graded, I am just thinking out loud, right. So if I encounter such a problem, so when I do research, what is a possible solution that I can envision. So there are all these interfaces, right. So I will design my material such that these interfaces are what are called diffusion barriers, right. So I do not let any diffusion happen through interfaces. These interfaces, if I make them diffusion barriers, right, if I do not let diffusion of atoms happen through interfaces, then I can create a material, create and sustain a robust energy material, right. So this can store dielectric energy, so which stores dielectric energy, right. Then my problem is, what are these diffusion barrier layers? Okay. Now, one thing that comes to my mind, I am not sure if anyone has done this, is I have a substrate. Let me not make the substrate silicon. I have a substrate, I have my first layer, right. So of BEST some 0.08, then let me just entertain me with this idea, right. So let me just put a diffusion barrier layer which happens to be graphene. Why graphene? I will tell you very soon, right. So I am trying to answer this question, right. So it is a design materials design, how am I thinking about materials design. Then I put BST 0.1 and I put another layer of graphene, right. So at this interface, then I put BST 0.14 and I put another layer of graphene, or maybe an electrode, it does not matter, right. So a graphene or some sort of an electrode on the top. Okay. Now I learned, right. So I learned that so graphene would not even allow water molecules to pass through them. Or I mean it would not allow, I think helium or something, I am forgetting what it is, but the graphene so has this sort of a structure. Sorry. Okay. So I have to again draw graphene carefully. Let me, this sort of a cage like structure, right. Now these are all carbon atoms, and it turns out that you cannot fit even small molecules into this, so if something should diffuse, it should diffuse through graphene, right. So through this hole here, right. Now if I make very good quality graphene and then I do not allow any sort of diffusion, right. So graphene cannot even let something like water molecules pass through it, right. So that is why people are trying to make these graphene barriers which will not let things be affected by moisture, right. So even moisture cannot pass through it. So as a result, you are assuming that tin atoms or titanium atoms, moisture meaning H2O molecule, or graphene has this property that I think even helium cannot pass through it or something like that. One of the smallest elements cannot pass through graphene, helium atoms cannot pass through graphene. So tin atoms or titanium atoms which are clearly larger than helium atoms cannot pass through graphene. Okay. Now I am just making this up right here, right. So but I am telling you how I am thinking about design of a material that would require high dielectric constant. I have designed it by saying, okay, so let me combine different materials of different phase transitions, right. So in the form of a thin film, right. So that I can measure capacitors, right. And then I have a problem here of so I have a problem that this thing will degrade with cycling, right. So, now I have to solve the degradation problem. For degradation problem I think of diffusion barriers, and the first diffusion barrier that came to my mind today while I am talking to you is graphene, right. So, because I learned somewhere that graphene would not even let moisture pass, or would not even let, if I remember correctly, helium pass through it, right. So, now I go to the lab and try to make these sort of materials and see if it works, right. Simple. So, this is how I am thinking about material design all the time, or so first I read literature. If my hypothesis that graphene would not let anything pass is correct, then the problem becomes how can I get this high quality graphene, right. So, which does not have any defects or anything like that, that would arrest the diffusion, or if graphene is not the option, what are the other options, right, and then I design my material based on that, right. So, but the basic principle remains that I need to keep these materials at their phase transition, at their particular phase transition temperatures, and I need to maintain this broad base of phase transition. Okay. So, so that is how I go about looking at the design, okay, so of various materials. Now, the phase transition, as we have seen in case of PZT, can also be not just with temperature, but it can be with composition, right. So, here there is another material called PMNPT, right. So, this I just briefly mentioned what is called a relaxer material. Here so I am at this, again this is sort of like a morphotropic phase boundary, right. So, where I am between two different phases, I have a CM phase coming up here, right. So, I can have polarizations in several directions, and because of that so I can enhance the susceptibility, and this is so sort of temperature independent, even from -100 to +100. If I make my material at this, my PMNPT at this composition, right, I have a large susceptibility. Rest assured I will have a large susceptibility, okay. Or I can so depending on the composition of lead titanate, I can have again different sort of these peaks, and I can combine all these materials to make even larger temperature stable PMNPT with diffusion barriers, right. So, this is how I go about designing materials which have large properties of my necessity, right. So, if I want to make really these are dielectric constants, if you look at them, right. So, these are dielectric constants like 15,000, right, 10,000 and so on and so forth, huge dielectric constants, right. So, they are useful for energy storage applications. Okay. All right. So, with that I think this is enough about thermodynamics. I think by the end of this module you have a feel of so how thermodynamics and equilibrium properties, right. So, if I understand the origin of these equilibrium properties, be it susceptibility, be it a coupled property such as piezoelectric property, right, then I actually microscopically understand what is the origin of this, and then so I end up designing materials such that I enhance the properties, or I may in some cases I may need materials with very low dielectric constants, right. Then I go far away from phase transitions. I use something like silicon oxide or something like that, which does not have so much of polarization fluctuations, right. So, once I understand the physics of it, I will use it to select my materials. So, initially I was just selecting a material, right. So, in this example I was just selecting PSN that already exists, but so in other examples I can I was actually designing material heterostructures or of my choice, right. So, how can I enhance the properties, how can I reduce the properties, right. So, thermodynamics tells you something about this, right. So, from statistical mechanics framework, okay, about the equilibrium properties. So, symmetry tells me what properties exist or does not exist, and what are the tensor elements that I should care about. Thermodynamics tells me, okay, what is the origin of these properties and how can I so how can I make it large or small, right. Aluminum nitride has a D33, right. So, D33 is a piezoelectric tensor along the third direction, right. So, 333 D333 in the Voigt notation it is called D33, that is about 6 picometer per Newton. PZT has a D33 that is about 600 picometer per Newton, or even it depends on which literature you see, but so it is an order of it's 2 orders of magnitude larger, right. so why is that contrast? Symmetry arguments do not tell me why I have this contrast. It is the thermodynamic arguments that tell me why I have this contrast, and what is a suitable material for what application, right. PZT I will use for applications where I will need to amplify, right. So what are called actuator applications. Aluminum nitride I will use for applications where I need so the losses, we will talk about losses in the next module. Losses in aluminum nitride are very small, right. So I will use it for applications where I need high equality factor like quartz, right. So quartz crystal to keep time, etc. I need really high quality factors. Okay. So this will take us into the next module where I need to understand the other aspect of material properties, which are not just how, it is not just about enhancing the properties, but it is also about looking at the losses, the dissipation in properties, right. So that will take us to kinetics, and in the next module I am going to, in the next class I am going to start about the dissipation module or kinetics. Okay. So thank you for your attention, and I will see you again in the next class with a fresh new module. Okay.